Go. Hello and welcome back to Calculus 1, section 3.3 on rules of differentiation. What? Differentiation. What does that word mean? What is the meaning of the word differentiation? Differentiation is a process of taking the derivative. So, differentiation is the process of taking the derivative of the function. Or you can say taking or obtaining the derivative. Taking or obtaining, whatever, obtaining here. Obtaining the derivative of the function. Now that process used to be that long limit with h goes to 0 and f of x plus h minus f of x, right? You all had that, I believe, as a problem 4 or whatever. And now we're just going to make the same deal like we had for multiplication tables. We're going to say, you guys know the definition of the derivative using the limit. Go ahead, use it for all problems. Or memorize the shortcuts that I am going to give you. You did this before for multiplication table. Can you add 7 8 times? 7 plus 7 is 14, plus 7 is 21, plus 7, right? 28. You can go and add 7 8 times. Or you can invest time and memorize that 7 times 8 is
56. And
then you don't have to do the addition. So you made this trade-off. Well, someone else made it for you because you were too young, but right? There was a trade-off. You either for your entire life get to repeatedly add numbers, or you get to memorize multiplication table. I am making the same deal to you today. You can either take all of your derivatives using the limit, or you get to memorize the formulas that I give you today. So these formulas are shortcut methods for you to memorize so that you don't have to do the limit definition every time when you need the derivative. So what are those formulas? First formula is derivative of a constant is 0. Right? So the derivative in respect to x of a constant is 0. This is the first formula that you memorize. So we can talk about it, why this is true. Why is the derivative of a constant 0? Excellent. Constant, yes. Constants are numbers. Numbers do not have change in them. They are graphed as horizontal lines whose slope is 0. Slope of that line is 0 everywhere, therefore derivative is 0. So constant, that word implies no change. So if you are trying to measure the change in something there is no change, the answer is 0. So the examples, what's the derivative of number 3? 0. What is the derivative of pi? 0. What is the derivative of 1/2? 0. So we are memorizing the formula that derivative of constant is 0. Then we are moving on. The derivative of x to the n is equal to n x to the n minus 1. What is this good for? Polynomials. Very good. X squared, x cubed, x to 100. Right? Can you imagine using the limit definition of x to 100 and then foiling your x plus h to 100? Yeah. While we all have our break and do nothing, you will still be working through the break to get x plus h to the 100 and then just cancel it, right? So this shortcut method will deal with all of that, skipping all of those limits. But you know what's beautiful about this formula? There's more to it. Yes, it will take care of the derivative of x to the 7, right? That's your n is 7, so you drop 7 down and then you get x to the 6 as 7 minus 1 is 6. Very simple, right? What else is under this formula? How about the derivative of the 5th root of x? Same formula does it. Why? Excellent. You can use your superior algebra knowledge to write this as x to the exponent of 1/5. Now your n is 1/5. Plug that everywhere and get your 1/5 x to the negative 4/5. You are just subtracting 1. So all of those questions are taken care of by, so we have polynomials and now we have radical functions. One more type, rational ones. 1 over x to the 10. Talk to me. X to the negative 10, beautiful. Which is negative 10 x to negative 11, which is negative 10 over x to the positive 11 at the end. Now you see all three flavors, all three types of functions that are covered by that one formula on top, which is x to the n. You have all of your polynomials. They include x squared and x to 100. Then you have your radical. Square root of x is in that pile. 5th root of x is in that pile. And then you have your negative exponents. So anything that has the denominator x to the 1 over x squared, 1 over x to the 3. And we did example for 1 over x to the 10. So we covered constants. We covered polynomials, rational, and radical functions. What's left? Well, our friend e to the x. What is the derivative of e to the x? Yes, it's itself. This is the only function in the galaxy, right, in the universe, that has this feature. Derivative of e to the x is itself. Now, most of the time, you are going to run into e to the 2x, e to the 5x, e to, some of those. So we are going to learn later in this chapter, I think it's 3.7, we're going to learn how to deal with that. So now we have a formula which you can avoid once you get there. And that formula is, so it's like a offshoot of this. The derivative of e to the ax, this a being a number, is going to be a e to the ax. So I will give an example. What is the derivative of e to the 3x? 3e to the 3x. Very good. So this a, which is in front of x, is now 3. So you get in the answer, for each a, you get to plug in 3. Do we all get that? if this a over here is 3, then these two a's must be 3, and they are. Are we all agreeing on that? Good. So we have all of those. Now we have something special, and these are rules. Properties, whatever. And we have 3 of those. Number 1, the derivative of sum of 2 functions is the sum of the derivatives. This is the rule that allows for differentiation of multiple terms, one at a time. So if I had the derivative of x cubed plus e to the x, how about e to the 2x, I can differentiate x cubed separately from e to the 2x. And that will be 3x squared plus 2e to the 2x. So this rule says, that was a good effort. This rule says that you are allowed to differentiate each term individually. You are not allowed to do this for multiplication, but for addition and subtraction you can. Next rule, same rule with a minus sign. So now for subtraction we have the same rule, it's just going to have a minus sign in it. And finally, rule number 3 says that if you have a constant in front of your function, you can kick that constant outside of the integral, just like limits. So if you have a constant times a function, you can kick constant outside and then just worry about differentiating the function. This rule is extremely useful, and you will use it all the time. So if you have to differentiate 5x squared, 5 goes out, and you are focusing on differentiating x squared, which is now 5 times 2x, which is 10x. Now clearly, as you do many problems for the homework and so on, you will immediately multiply these 2 into the 5, make it 10, right, and go from there. So there you have it. These are your rules. We are going to have a special section, separate section, to cover trigonometric and inverse trigonometric, right? So those are going to be 3 point something and 3 point something, all right, later on. So for right now, we have these basic ones. So now, are you ready to solve a problem that says derivative of 4x squared plus 9x minus 6? And the answer is hopefully yes, you're ready. You know that you can ignore the 4 and just focus on differentiating x squared. What's the derivative of x squared?
2x.
And then times 4, 8x. Plus derivative of 9x is, and derivative of negative 6 is 0. Great. How do you check this work? How do you check this? Sadist.
Use the computation function?
No, use the computer. Type in.
Oh,
Yeah.
okay.
You go Wolfram Alpha and say differentiate, and it does it for you. Right? Oh, really? You were completely unaware that computers do these things? All right.
How can you check it, like, for real though? Like, if it's like on a test and I want to check my answer?
No. You get to do the limit for like 35 minutes, or yeah, or you just say, I learned this, so it's good, right? It's okay.
How did you say they check it on a computer?
So for the computer work, the beautiful thing about Wolfram Alpha, or if you have Mathematica installed, is you talk to it. So let me give a quick tutorial. We're going to go into Wolfram Alpha, and once you are on the website, just talk to it. Derivative of square root of x raised to the 7, whatever. You can do anything. It will interpret your words as a mathematical. So you clearly see what I typed. Derivative of square root of x to the 7. It gave you, and then it gave the derivative of it. If you want to start simple, x derivative of x squared, it will give you 2x. We haven't covered yet derivative of sine x. It will give you cosine x back. So talk to it, right? If you need to check any of your limits, limit of 1 divided by x minus 2 as x goes to 9, right? So just talk to it. It's an AI. It listens on the other end and provides the answers. It's like a magic ball, right? You had this and you go back in time, you get burnt on a stake in the middle of a square as a witch, right? So this is the way for you to check all of your homework exercises and everything you do as you practice. Now, obviously, if you cheat with this, you learn nothing, and then, right, exam 2, and we're out. So that's Wolfram Alpha. There are other, if you pay them money, they're going to enable this step-by-step solution at the end. Let me see if this I typed in Advil. No, it works. In case you want to make it at home, I mean, they give you everything you need.
Right?
And they give you all the specs on it, including the biological half-life. See, 1.9 hours for half-life, which is why you take Advil every 4 hours. right? You wait 2 hours for half of the dosage to wear off, and another 2 hours, the half of the half. So your system will only contain a quarter of a dose you took. Then you take another dose. So now you have a full dose and a quarter in your system. Every time you take a medication, next time around, you end up with more medication in your system, which is why it's so easy to overdose with medication. Half-life means the half of the thing that it's in you is going to be gone, regardless of how much you have. That's what the half-life is. So the medication never goes out, actually. Yeah.
Never?
Never.
Never.
It's exponential decay.
Right.
Yeah, but it's got to hit 0 in that.
In the infinity,
right?
yes. In infinity. You're going to last that long? Ah. You're not an elf.
Tell me that every single thing I ever put in my body is still there.
Yes.
I don't believe you.
Extremely small percents that are probably not affecting you in any way, but yes.
Then why do they talk about like with like different drugs, like, oh, it takes 2 years and then you're done?
Because they don't know math, I guess. I don't know. Exponential decay formula is clear. It will reach 0 at infinity. So if the exponential decay looks like this, which is what you have for the half-life, when you take your 500 milligrams over here, this timetable here says mass is equal to 0 at t equals infinity. So good luck waiting. There we go. Beautiful, right? Way to ruin my day. And you are welcome. All right. I knew I should have skipped this class. So there's that. Now let's take a look at the derivative of. Let's put something. How about, yeah, spicy. How about 10 divided by square root of x cubed? There's a beautiful example. Use some algebra to rewrite this monstrosity, and then, as Nike would say, just do it. I'm serious. That's what I say.
About why 9 doesn't have an x attached to it in the first one.
Because the derivative of x is 1. This is not, so this is related to the previous example. You have, if you just worry about the derivative of x, because you know what happens with 9, right? That it's x to the first power. Would you agree?
Yeah, yeah.
So now your 1 goes down, and then x to the 1 minus 1, which is 0. X to the 0 is then 1 times 1, which is 1.
Got it. Okay.
So anytime you have a single variable, you differentiate the single variable, it goes to 1.
Okay.
So technically it's just like, oh, it disappears. But it's actually x to the 0 over here, and x to the 0 is 1, so there it go. All right, can anyone help me over here to rewrite this problem? I should say 10.
Take the 10 out.
I'm sorry, I almost got my eye scratched out. Okay, I am gonna put 10 out. Good, there we go. Whew. Wow. Now what? X to the minus 3 halves. Thank you. So this is the spiciest it can be. Obviously, you can have different numbers, but if you think about this, we have a square root, which is a half. We have it in the denominator, which is a negative, and then we have a positive exponent 3, which is the top of the fraction. So if you have an issue with algebra, this is a perfect example to see all 3 of those rules in one spot. Being in denominator is negative, square root is over 2 over there, and 3 is 3 on top. So now you have your n as negative 3 halves, and you just proceed from there. So 10 times negative 3 halves times x to the negative 5 halves. Because negative 3 halves minus 1, that's a common denominator, right? So minus 3 minus 2 is minus 5. At this point, 10 and 2 cancel. So we have negative 15 over, you can say square root of x to the 5. That's fine. To put it back in the form to practice even more. Green? If you have any questions, this is the perfect opportunity to ask those questions. Because we cannot have these basic skills be shaky in any way. Because the rest of your calculus, all of it, depends on these first steps. No more limits. So we're going to live with this in every course from now on. Yes?
I have an algebra question. Why is the 10 being multiplied?
Well, the 10 is the numerator, right?
Yeah.
So it comes out, so that's that 10, and then it cancels. When you are dealing with fractions, the numerator multiplies, denominator divides. So as you are looking at, let's say, 10 over x, this is 10 times 1 over x, because you can write it as 10 over 1 times 1 over x. You multiply across for 10 over x. So anytime you have a number in the numerator, you can bring it in front and keep 1 if you want to separate the function. So that's the algebraic manipulation in terms of the way the fractions and the fraction multiplication works. You're welcome. Any other questions, concerns? Yes?
Where did you get the 5 from? Minus 5 over 2.
The formula is x to the n minus 1. So I have negative 3 halves, which is n, minus 1. To find the common denominator, negative 3 halves minus 2 over 2, negative 5 over 2.
Got it.
And I'm just going to bring the textbook up and take a look at some of the homework exercises from the back. No coffee. Accept cookies and close. Of course, but I know where's that gonna go. Nowhere. As if they're gonna send cookies ever. Hello. Some advanced algebra over here. All right, the next question. All right, so here is the next question that we need to address. The derivative of x squared plus 1, everything squared, like this. What do we have to do first?
Square.
Yes. We have to foil. There we go. Foil. We have to foil, and then we will be able to... Yes. So what do we have? d dx of... When we FOIL, we get x to the 4th plus 2x squared plus 1. You can multiply these on the side if you don't know the a squared plus 2ab plus b squared formula. And now you can quickly differentiate 4x cubed plus 4x plus 0. And we also have to talk about something very important now. And that is when my brain stops like this, the other F word. Factor. Good. So 4x, x squared plus 1. You have foiling and factoring that we are using. So we FOIL because there is another math rule for differentiation that we will use when this exponent over here is 70, right? If it's a square, it's a quick FOIL, so it's not a big deal. If it's a cube, it already becomes annoying. When you present the answer, if the answer can be factored, you should factor it every time, because chapter 4 is coming. All right? In chapter 4, all of these problems become a first step of a much larger problem. And in that larger problem, you will have to set this equal to 0 and solve the equation. So if you don't have it in a factored form, where you can set each one of these to 0 and solve them easily, it becomes much harder work, right, for us. So getting used to factoring your answers now is something that will greatly help you later on in chapter 4. So anytime when you can factor, factor and leave it. Now, both of these are 100% in your exam too, but this is a much better answer because chapter 4 is coming. Let's take a look at another. Here's another one. DDS, because now variable is s, of 12s cubed minus 8s squared plus 12s divided by 4s. What should we do here? Exactly. Divide or reduce. So we have our algebra question to deal with first, and then we do the calculus. So copy the derivative part, and now 12 divided by 4 is 3. S cubed divided by S is S squared. Minus 8 divided by 4 is 2S. Very good. And then plus 3. And now we take our derivative. Derivative of 3S squared is 6S minus 2, and derivative of 3 is 0. Good. Great. There is one more concept here, and then we go to the break. And that is higher order derivatives. So, do we agree that if I take the derivative of x cubed, I get 3x squared? Do we agree that this is also a function? Can I differentiate again? Yeah, why not? So, when you repeatedly differentiate each function, you go from first to second derivative, to third derivative, to fourth, fifth, 6, you can go mathematically as far as you want. So we would say higher order derivatives. We usually use a different notation because Leibniz notation gets to be a little bit confusing. I'll show both notations. But generally we use f of x is x cubed, and then we say f prime, which is the derivative, is 3x squared. For the second derivative, we put double prime, and that would be what? 6x, very good. The third derivative is 3 primes up there, and that would be 6. Now, the fourth derivative and everything behind that is changing the notation to these parentheses where you write the number. Because you really don't want to go into a 20th derivative and do this. You know, because, yeah, we all hopefully understand that. So what would be the fourth derivative? 0. How about the fifth derivative? And how about 173rd derivative? All zeros, right? So does this mean that all of your derivatives will be 0 if you go sufficiently far out? What do you mean, oh?
Eventually.
Eventually.
And then I was like, thinking about it.
Okay, let's try this one. So, if f of x is e to the x, what is 1374th derivative of e to the x? Wow, you guys are experts in taking 1374 derivatives in a row in a split second. That's awesome. So, it depends on the function. Yes?
Conceptually on a graph, what does that mean? Having a second derivative or a third derivative?
Oh, great. We're going to have sections upon sections upon sections dealing with that. I will give you an example of a position function, which would be the location of a particle or a person or a mouse leaving the room, which would be a graph on the floor. the first derivative of that function would be the velocity function, how fast you left the classroom. The third derivative, the first derivative is the velocity. The second derivative would be acceleration, because as you can see right now, my speed is 0. In order for me to go to the printer over there, I have to change my 0 speed into whatever speed so that I can cover the distance. The third derivative is called jerk, which is how fast you change acceleration. You experience that in your car when you push your gas pedal or your brake pedal too fast. The change in acceleration is called a jerk, and that's your third derivative. There's more after that. So these are the simplest ones to understand. So your first is the function, the position function. So it's much easier to understand these concepts when you have what they're designed for. Isaac Newton said the second derivative is gravitation, which is right, and it all worked out nicely for him, and now he's immortal. Leibniz did the same thing, but he did it for business and economics, and no one cared, right? So he doesn't get the same fame as the one who did it for physics, right? But they did it at the same time frame, within like 2-3 years of each other, and they had the same results. I prefer Leibniz notation over Newton's notation. So we are going to take multiple derivatives. In terms of a graph, we are going to have increasing, decreasing, that's the first derivative. Then we're going to have concavity, which will show which one of two increasing graphs has a better investment potential if you're investing money. So we'll talk about those things in chapter 4. Right now, we're talking mechanics. So right now, you just know that you can take 100 derivatives if you want to, and then for some of those derivatives, we'll have application later on. We're done. That's the wrap on this lecture. Let's take a break. When we come back, we have product and quotient rule. Because you remember these rules over here? If you look at the rules 1 and 2, they only have addition and subtraction, right? So we need to address product and quotient. And that's next lecture. So see you in 5 minutes.